So what I want to do now is I want to compute this expression for every j. So it's the sum over I, so it always runs over all the i's, and I want to compute it for every j. So what does it mean to compute it for every j? So to remind you, this is the shape of the x. So the x is 3 by 323. That's because each x for each case is 3-dimensional. Really, it was 2-dimensional. Then we added the 1 in order to get rid of the bias. And there are, in this case, 323 test cases. So the x is 3-dimensional, and the w is also going to be 3-dimensional. So for every j in 0, 1, and 2, we want to compute the derivative of the cost function with respect to the wj. And that's what this expression does. So let's first deal with just the one j. So let's set j to be just 0, for example. And now for the given j, we'll just compute the sum over I. So over all the training cases, or all the cases in the mini batch, as the case might be. So how do you compute the sum? Well, what we'll do is we'll define an accumulator variable s, set it to 0, and now we'll just go over all the i's. So I'll say for I in range. Now what should the range be? Well, the range should be the number of test cases, which is this guy, which is x shape at 1. And what I'll do now is I'll just accumulate this expression. So it's going to be s plus equals x. So here it's the jth coordinate of x for the ith training case. So the j goes first because that's the jth coordinate. And this is the first coordinate here, the 3. Xj at I times, here we have basically the dot product between w and x. You can look at it as matrix multiplication as well, of course, of just one-dimensional vectors. So let's write it like that. So it's going to be dot theta transpose x I like that, minus y I. So it's going to be the output for the ith case, that's yi, and that's the prediction for the ith case. That's going to be just w, or in this case theta, dot x. All the dimensions are used, so 3 dimensions are used, but for that particular training case. And now at the end, what we want to do is we just want to multiply the s by 2. So this is how you would compute the thing for a single j. Now, of course, we want to compute it for all the j's. So in order to do that, let's first initialize the derivative that we want to compute. So what we want to compute is we want to compute dc by d theta for theta 0, theta 1, and theta 2, because there's 3 of them. So 3 of the thetas, which is the same as saying 3 of the w's, just different notation. So we'll initialize them all to zeros like so. So we have a function zeros, which creates matrices of zeros. And what we want is we want dc by d theta to be the same shape as the theta, because it's going to be dc by d theta 0, dc by d theta 1, dc by d theta 2, which is exactly the same shape as theta 0, theta 1, theta 2. So now we can get rid of this thing and substitute dc by d theta at j over here. Here it's also going to be dc by d theta at j, and all we need to do is we now need to repeat this for all the possible j's. So the way to do that is to say for j in range, so what's the range going to be is we want this 3, which is just x dot shape at 0, for example. The more straightforward thing to say would be just dc d theta dot shape 0, because that's exactly what we want. And all that's left to do now is we can now get rid of the j equals 0, and we can verify that the thing that we computed is the same thing as what you computed in tutorial. So let me quickly compute this. dc by d theta is going to be like that. And if you compute what you did in tutorial, you'll get exactly the same thing.